Right, here we are with section 1.3. You'll need to have your books with you while you're taking your notes because I'm going to be referring to several tables and charts in your book. So please be sure you have your book and your notes ready to go. So today we're talking more about functions and graphs, and we're first going to talk about increasing, decreasing, and constant functions. And if you'll please open your books to page 165, you can see that at the bottom of the page there is a chart talking about increasing, decreasing, and constant functions. When we talk about increasing or decreasing, we are talking about whether the function rises as it moves from left to right. That would be an increasing function. Whether it falls as it moves from left to right, and that would be decreasing. And then obviously if it is neither rising nor falling, that would be a constant. You're familiar with this when we talk about linear functions. Y equals mx plus b. If the leading coefficient m is greater than 0, this is a rising or increasing function. If m is less than 0, this is a decreasing function. And if m equals 0, that makes it a constant, like y equals 2. So increasing, decreasing, and constant functions. If you want to take a minute to look at the examples on page 166, go ahead. The next topic is relative maxima and relative minima. And again, if you'll look at the bottom of page 166, you can see a graph that they have shown in the book. Looks something like this, and it talks about relative minimum and maximum values. Now, a maximum or minimum is the greatest or largest y value. When we talk about values, we're talking about when we're talking about function values, we're talking about y values. So if a graph has a max or a min, maximum or minimum, that's the largest or smallest y value. Sometimes a function, however, has a relative max or min. On this example, this point here would be a relative minimum, because in relation to the other values near it, it is the low point or the lowest value in that area. Conversely, the value up here would be your relative maxima. And although it's not the highest value on the entire graph, because the graph does keep rising to the left, it is, for its particular area, a maximum value. When we talk about any of these things, function values, we're always talking about the y values. Where is the graph the highest or lowest? So these are our relative maxima and relative minima. Again, take a minute and look at the text if that would be helpful to you. The next topic is even or odd functions. There are some definitions on page 167. I've copied them here. A function is even if f of negative x is the same as f of x for all x in the domain of f. An odd function occurs if f of negative x is the opposite of f of x for all x in the domain. I'll give you an example of both of these in just a second, so go ahead and take time to write your notes down. So for example, if we look at the function y, well, let's actually use f of x. F of x equals x squared. If I calculate the value of f of negative 2, I will get 4. That would be my f of negative x. If I calculate f of 2, I still get the value of 4. So this is an even function because when I look at a negative position versus a positive, I get the same value. This graph, of course, is a parabola passing through 0, 0. And this is an even function. So if I plug in negative 2, I get the same value as I plug in positive 2. A simple example of an odd function would be f of x equals x cubed. Here, if I look at f of negative 2, I get negative 8, where f of 2 equals positive 8. In other words, if I change the sign of the input, or x value, it changes the sign of the output as well. This particular odd function looks like this, and so if I plug in f of 2, I get a positive. If I plug in negative 2, I get a negative, and this is called an odd function. To determine if a function is odd or even, we're simply going to substitute negative x for x. So pause the video to copy this down. Okay, so f of x is x cubed minus 6x, and we want to look at what do we get if we plug in f of minus x. So instead of choosing a specific value, I'm going to choose all negative x values for any x that we can put in. If I plug in negative x and cube it, and plug in negative x here, my result will be negative x cubed, because a negative times a negative times a negative is negative, and positive 6x. So looking at the original function and at the function with negative x substituted, we can see that these two are opposites of each other. In other words, if I put a negative in front of the original, I will get the function from plugging in a negative x. So every sign in the original function has been changed. The positive x cubed becomes negative x cubed. The negative 6x becomes positive 6x. Therefore, f of x is exactly the opposite of f of negative x. This is an odd function. Let me give you two more examples that you can look at. If you missed some of that, just pause and rewind. Take these two functions, plug in f of negative x, and see what results you get. If the signs are all changed, in other words, if f of x becomes the opposite of negative f of x, it is an odd function. If the function remains exactly the same, it is an even function. So take a moment to try plugging in negative x for x in these two functions. In the first example, if I plug in negative x, when I raise a negative x to an even power, it becomes positive, and we can see that the resulting function is exactly the same as what I started with. So substituting negative x for x does not change the function. That makes this an even function. In the second example, when I plug negative x in place of x, we find that some of the terms have changed signs and some have not. This is neither odd nor even. In order for it to be an odd function, our f of negative x has to change all of the signs. In order for it to be an even function, all of the terms have to remain exactly the same. And if some of the terms change signs and some do not, this is neither even nor odd. When we have an even or an odd function, they are symmetrical. Even functions, like the first example I gave you of y equals x squared, are symmetrical around the y-axis. every x value has an exactly the same corresponding negative x value. Odd functions are symmetrical around the origin. In other words, if I flip the first quadrant into the third quadrant, we can see the symmetry. Even functions and odd functions. We can find them graphically by seeing if they're symmetrical around the y-axis or the origin, or we can find them algebraically by plugging in negative x in place of x. The next type of function we're going to look at are piecewise functions. These are functions that are defined by two or more equations over a specific domain. And I'm going to back up and pause on this for just a moment. We'll hold off on this second part. Write down the first piece of information here. The way we typically see a piecewise function is something like this. F of x equals x plus 1 when x is greater than or equal to 2, and maybe 2x minus 3 when x is less than 2. I'm going to step down here for a moment. So if I were to graph this, we all know that x plus 1 is a line that begins at 1 and has a slope of 1, but I'm only going to graph this when x is greater than 2. So when x is 2, I would have a y value of 3. When x is 3, plugging into the top again, I would have a y value of 4. So starting at x equals 2, this part of the graph would go like this. The second part occurs when x is less than 2. Well, what happens when x is 2? If I plug in 2, I get 4 minus 3, which is 1. But I want just less than 2, so I'm going to use an open circle there. When x is 1, plugging into this equation, I get negative 1. When x is 0, I get negative 3. So the left part of the graph looks like this. These both happen to be linear functions. And you can see that it's a piecewise because it comes in two pieces. Okay, let's continue on. And again, this is shown in your book on page 169. So if you want some more examples, always feel free to stop and pause the notes so that you can look at examples in the book. If I haven't given you enough, or if you're not sure, rewind the tape or look at further examples from the text. The next example of a piecewise is called a step function. And for this one, I'm going to ask that you look on page 171. Sorry. So page 171. The step function is a specific kind of piecewise function where we have steps or stairs. And the example in the book is the greatest integer function. In order to write the greatest integer function, we do something like this, where we say that f of x equals either integer x, or we can denote it by saying f of x equals, and we use a kind of a double bracket, and this means that the solution is the greatest integer less than or equal to x. So if I am using this function, and I'll use the second one, where f of 2 equals, and then the solution is going to be the greatest integer that is less than or equal to this. So it would be 2. F of 1.5, what is the greatest integer that's less than or equal to 1.5? That would be 1. What would f of 2.3 be? Again, the greatest integer that is less than or equal to this would be 2. And if you look at the graph on page 171, you'll see how this is graphed. Okay? So that's called the step function or the greatest integer function. Just another